Okay, let's just start. Hi, everyone. Welcome to the second virtual MS seminar at UT Austin. It's my pleasure to introduce Francis Bach. Francis is a graduate of École Polytechnique, and he did his PhD at UC Berkeley with Mike Jordan. He's currently a researcher at Inria, and he leads the machine learning team, which is a part of the computer science department at ENS. Francis has received several awards. Of course, I'm not going to mention all of them. I'm just going to mention a few of them. He is the recipient of Inria Young Researcher Prize in 2012, ICML Test of Time Award in 2014, and the Lagrange Prize in Continuous Optimization in 2018. He's also a member of French Academy of Sciences, and today he's going to talk about some of his recent work on the convergence of gradient descent for wide two-layer neural networks. With that, I hand it over to Francis.
Okay, so thank you, Ariane, with a nice introduction. And also I would like to thank you for the invitation to visit Texas tonight. So unfortunately, it's a bit virtual this time, but I hope I can join like in a few, okay, let's say a few years to be on the safe side and enjoy Austin. So today I'm going to talk about joint work with Lénaïc Chizat, who was a former postdoc, was now a researcher at CNRS in south of Paris. And the idea today is to talk about like essentially two sets of papers we have worked together on trying to analyze gradient descent for neural networks. So let me jump to the to the setup. So we're going to consider classical supervised machine learning with like observations xi, yi. You can think of xi as being an image, yi some label, and we have n of those. And we're going to learn some prediction function parameterized by theta. So it's h of x and theta. X is the input and theta is the output. And I'm going to take d as the number of parameters. So there are typically two sets of functions that people are typically using in machine learning. The first one is linear predictions. So when you're linear in the parameter theta and potentially nonlinear in x through the effect of some feature map or some feature vector. And so typical examples are advertising and also a bit in genetics, where the feature vector may be very high dimensional. So D is large and N is also very large. This is working well for still a lot of problems, but for some problems, in particular computer vision, NLP, and many others, then those linear models are not best performing, and people reconsider now neural networks where you have a sequence of when you have like you take first one linearity theta 1 over there, and then you take a non-linearity sigma and you go along and you add more and more layers, and this is a non-linear function of your parameters theta, and this is what people typically use. So here, of course, I'm oversimplifying, as most of the models that people use for machine learning, for computer vision and NLP, have many, many more subtleties. There is like some pooling, some convolution, and so on. So I'm going to ignore this and focus mostly on the simplest example. All right, so the way those models are fit, so you consider, you form like the regularized empirical risk by taking a data fitting term, which is the average over your training data of a loss between what you want to predict, yi, and your predictions, h of xi, theta. And this is the data fitting term, and you add some regularizer to avoid overfitting. This is very classical, okay? So this has been around for many, many years. And so here, I'm going always to assume in this talk that the loss is convex with respect to its second variable. Okay, so most losses that you encounter in practice, even for deep learning, satisfy this. So least square satisfy this, logistic loss, multinomial loss, and so on. So I'm going to assume the loss is convex. So of course, this is just a mean to an end. So nobody really cares about minimizing this problem. We care about good generalization on unseen data, so the so-called test error. And this is where you typically assume that test data and training data come from the same distribution, P of xy. Okay, so I'll come back to that later in the talk. Our goal is not to minimize empirical risk. Our goal is to minimize the test risk. All right, so this is a classical parametric supervised learning setup that we're all familiar with. So it's convex in some cases. So the problem is convex. A sufficient condition is that you have linearity in the parameter theta. So this has led to a lot of work in the last 20 years or more. And the take-home message is that you have efficient algorithms to do that, like various versions of gradient descent or stochastic gradient descent. And you have very strong quantitative runtime and prediction performance guarantees. So before you even run the algorithm, you have an idea of how long it's going to take. Okay? So this is like true for least square, true for logistic regression. And so this has led to a lot of nice both algorithmic and theoretical papers. So this is what I call the golden years of convexity in machine learning. Okay, so I put the start in 95, like supervector machines, and I put the end in 2020. So we still have like a few months to go before the golden years stop. So I've mentioned like SVMs and kernel methods because this is where I studied machine learning. So this is what I know when I started. But since then, there have been a lot of other areas where convexity has played a major role. So this is true in machine learning, but also like in signal processing and in statistics. So sparsity as being an important aspect in the last 20 years. So optimal transport is also like a place where convexity plays a large role. And of course, AGD is one of them. So here I have a longer list when I have more space on my slide. And so many areas where convexity allows you to get like a good match between empirical performance and analysis. The problem is that this does not work for neural networks and for deep learning, where this assumption of linearity in the parameters is not satisfied. So the goal of the talk is, what can we do for deep learning? So this is the goal. So I'm going to consider a multi-layer, fully connected neural network, which is depicted over there. So as I've mentioned earlier, this is already a simplification compared to what people use in practice, which is like convolutions, pooling, and so on. And what I will show in the next slide, I'm going even to simplify a bit even more by just adding one hidden layer. Okay, so it will be the first neural network which is non-linear in the parameters, which is one hidden layer, so overall 2 layers. So what are the main difficulties? Well, there are many more, but the main I'm going to focus on today is the first one is that the problem the optimization problem is not convex, so it's going to be harder. And finally, since people tend to use very wide networks, so wide meaning that you have the hidden layers tend to be very large, then you get lots of parameters, and it's often called the over-parameterized regime. And in those setups, you have to be careful. If you have many more parameters than data points, you have to be a bit careful. And this will be also a topic of today's talk. So let's look first at the optimization. So what can go wrong? Pretty much everything, okay, if you go non-convex, because stationary points are not necessarily global optima, and you can have local minima. So it's a function in 2D. You have one global optimum over there, local minima over there, local maxima, stationary points. You may have some plateaus, which don't have so much here. So everything starts to be difficult. Okay? And so what people have started to do is trying to get local guarantee. So if I can't ensure that I get the global optimum, maybe I can be sure that I avoid like the local maximum. It's rather easy. But I avoid like stationary points like this one, which are not like local optimum. Okay? So this can be done with various versions of gradient descent, and very nice papers by Lee and colleagues and Jean and colleagues. But it's just local. Okay, this will tell you in my example over there that I'm going to converge to any of those 4 points. Okay, but nothing more. Then, as a bad news to start the talk is that you will never find some global performance guarantee in the non-convex setup. So if you just say, I want to minimize non-convex functions, then you have to be exponential in dimension. And the proof is just like one line with like one drawing. So if you minimize a function like this, which is always flat, except at a given point over there, with a local technique, you have to start your algorithm to be lucky and to start in the good region where it's not flat. And in high dimensions, the volume of the good region goes to 0 exponentially fast in dimension. So you are unlikely to get a global guarantee for non-convex optimization. So this is well known. And people, my colleagues would tell me that, sure, but who cares about minimizing that function? Okay, so nobody cares. People care about neural networks. So why not trying to specify your guarantees for neural networks? So this is the opposite, in a sense, as the field of optimization, which tries to be as general as possible. We're going to do the opposite, focus on a simpler problem, on a specific problem, which is like neural networks. So people have looked at it, and I think two sets of work have emerged. The first one by Choromanska and colleagues, where they've been able to highlight a class of functions for which the local guarantees, and being local guarantee meaning that if you can converge to a strict local minimum, then you're never far away in terms of like performance, never far away from the global optimum. Okay, so this is like very interesting, but the class of function is a random class of functions, and the link with neural networks is not strong enough to provide like guarantees on a given problem. Another set of work, also very interesting, by Sotanol, Kotabi, and colleagues, and others. For some like neural networks, you can show that there are no, like all the strict local minima end up being like the global optimum. Okay, so this requires like extra assumptions, for example, like quadratic activations, which is not what you want to do in the neural networks. So there are like other works trying to specify, to get like more guarantees for the specific case of neural networks, and we're going to follow the route by also working on a specific model. So what is this model? So this is the single hidden layer neural network, or often sometimes people say 2 layers. Okay, so layer 1, layer 2. And so the way it is going to be parameterized through two vectors. So one matrix theta1, which is the matrix of input weights going from the input x to the hidden layer. So this is a matrix. And you have the output layer going from the hidden layer to the output weights, going from the hidden layer to the single output node. So it's a vector. Okay, so and the way you can write it, and this is a key in the analysis that we are doing with Lénaïc, is to use the fact that the prediction function h is a linear combination of elements which have their own parameters. Okay, so each of those functions is parameterized by its own parameter wj, and there is no sharing with the other members of that sum. So here, in the context of neural network, wj is simply theta2 of j, the output weight associated with the neuron j, and theta1 j, which is the input weights associated with neuron j. So if I take this neuron, hidden neuron, this is the output weight, those are the input weights. Okay? And because of the setup, our prediction function is a sum of terms which have independent parameterizations. So this will not work beyond 2 layers, okay? Because if you have more than 2 layers, you start to have parameter sharing, and which is the whole goal of neural networks, is to do some parameter sharing. But this we cannot handle that case at the moment. So I'm going to focus only on the 2-layer case. Okay? The goal will still be to minimize the empirical risk, which we have, the risk which you have there. It could be empirical or expected at the moment. And the key here is that I'm still going to assume some convexity, and this is a convexity of the loss. As I've mentioned earlier, I consider this as being a weak assumption because this is typically used even in deep learning. So if you take a logistic loss, then or the least square loss, you always convex in H. Okay, I'm going to assume that. All right, so how are we going to look at this? We're going to have one simple insight, which is not ours, which is to look at the large M limit. So here, M is the number of neurons. And since we want to look at the over-parameterized regime, and if we believe that this over-parameterized regime has some magic, let's try to study the limit when M goes to infinity. And the the core intuition is that as soon as you replace this large average over psi of Wj by integral over some measure. So it's exactly equal if your measure over there is the empirical measure associated with your neurons by your parameters Wj. Okay, so this is inequality. And the idea is that when we're going to take m go to infinity, we're going to replace measures like this by densities, and which is common in physics. And this is really the main insight. The limit when the number of neurons goes to infinity is taking the limit in distribution of this to something which has a density. So this is a classical setup in various areas of applied mathematics. So I think this dates back from Baron, and there are probably earlier references. And there's a series of works showing that this is a nice idealization of the problem. So essentially what we have done here, we have replaced the parameterization in Wj. So we had m, we call them particles for reasons you will see for when you see the nice pictures. So I have m parameters of particles over there. And this is parameterized non-linearly in the particles because of the function psi, which is not non-linear. And you replace it by the measure, integral over a measure. Now, as a function of the measure, it becomes linear. Okay, so you have convex of a linear function. So you have essentially made the problem convex. And so this is where you say, oh, victoire, or victory, but there is a catch. And the catch is that you now have a convex problem over measures. R is convex, is your loss over a linear function of the measure. But the input, the measure, is an infinite dimensional space. Okay, so now you have transformed your like finite dimensional problem, okay, to an infinite one. It's convex, but it's still not there. So of course, we know how to work with large spaces in convex optimization. And one way is to do Frank-Wolf techniques. So this is typically used a lot when you have when your constraint set that you want to optimize over is a convex hull of many points. Okay, then you can use Frank-Wolf techniques to essentially build your point in your convex hull as a convex combination of a few atoms, and you build the atoms one by one. Okay, so this is a usual Frank-Wolf algorithm. And so you could do this as well here, but the issue is that to decide which point to add, you have to solve some optimization problem, which is as hard, which is like an NP hard in general. So you have replaced your hard problem by a sequence of hard problems. So at the end, this is not really useful. And it is, I explained this in a like paper from 3 years ago. And anyway, this is not what people use in practice. Okay, so people have tried a bit to do incremental learning of neurons, but at the end, most people use gradient descent. And this is why we're going to study this today. So this corresponds to go back to my set of particles. So mu is going to be a set of Diracs, and I'm going to use gradient descent, okay, which is called a backpropagation in that setup. Okay, so this is what I'm going to do, trying to let the number of particles go to infinity. Okay, so there are 3 questions which are associated with this. The first one is, does it tend to something? Okay, so does it mean anything to let the number of particles go to infinity? Does this intuition that going to a measure make sense? So this would be the first question. The second question is, can you show anything about the convergence of this algorithm? Okay, so, and this is what we're going to show that in the large M limit, you get global convergence of a form of gradient descent. And finally, you know how to optimize it, but can it generalize? Okay, so because since you take a lot of neurons, you may have a very like bad overfit. So let's look at those questions one by one. So the first one, okay, I've worked on it with Lénaïc Chizat like 2 years ago. So just a reminder of the generic setup. So this goes beyond neural networks. Okay, so whenever you have a function of a measure, which is a convex loss of the integral over the measure. Okay, so this you can apply what we're doing. So this applies to neural networks, but this applies as well to spike deconvolution and other applications. All right, so we're going to minimize directly using particles. So we're not going to parameterize it like a screw measure. We're going to take the average over like the psi size of Wj. And so other simplification is going to consider the gradient flow. Okay, we're not going to consider the algorithm where you take a step towards a negative gradient. We're going to consider the ordinary differential equation where we have this one, like the gradient, the derivative of W is minus the negative gradient of our cost function. So it's like the steepest descent curve that we're going to draw over the problem. And so this is known to be some idealization of SGD. Okay, so SGD has been around for 50 years, and the first analysis, in fact, of SGD were a lot relating them to those gradient flow. And of course, here, this is like all fuzzy, and with no, to make this like formal, it takes a while. But I think the take-home message is that if you do single pass SGD, okay, so if you take, you get data. So if R is your classical risk, and you observe like samples, you do single pass SGD, then you can show that with many assumptions that if the step size goes to 0, then you're going to follow the gradient flow at the end. Okay, so this is, of course, you need to get the step size to be small and so on, but this is one reason why gradient flow is interesting to learn. And the beauty here is that with a single pass SGD, you're doing like, you have test time guarantees. But this is not what people do in practice. So if you do multi-pass SGD, so you take your data points over and over again, then you start to minimize the empirical risk, and you converge then you follow the gradient flow if you have a step size that goes to 0. Okay, so here, clearly here, I'm hand waving my way through the use of gradient flow. Okay, so we are lazy. We use gradient flow because we can prove things. Hopefully, we can extend to gradient descent in later works. But to me, this is one like a theme for this talk is that we simplify the problem over and over, trying to get something which at the end will be very qualitative. When you compare to what we had for convex minimization, which was super clean, you have an algorithm, you show how it works. Here, it's not as nice as this. You simplify, and hopefully you get something out of it. All right, so we're going to study gradient flow. And the limit, now the question is, what is the limit when m goes to infinity? And so this has been in fact looked at by people before, and nice work by Nintendo and Suzuki, and so Lénaïc and myself, but by also nice papers by a team at Stanford, and also people at NYU, and I forgot where those persons are, but it's also very interesting work. And so the idea that it has a limit, and this is related to gradient flow over distributions, which is not surprising because when m goes to infinity, I'm going to have like distributions which move along, and the good metric to do the gradient flow is the Wasserstein metric. So this is, if you want to know more, you can look at the papers. So here I will not go too much into the details. So it has a well-defined limit, and the goal is to study this well-defined limit, and which is a gradient flow over measures. So the limit, it does exist. Then does it converge? Okay, so here, what will be the informal theorem? And as you can see, I'm trying to hide all the technical assumptions. So the theorem will be when the number of particles go to infinity, okay, then we converge to the Wasserstein gradient flow, and it turns out that this Wasserstein gradient flow can converge to the global optimum. Okay, so here, what's important and a bit subtle is that if you go back one slide, this problem f of mu is convex in mu. Okay, so if you take any algorithm which use convexity in mu, typically any stationary point will be a global optimum. Here, when you look at the Wasserstein gradient flow, it does have some local optima. And in fact, this is well known in the neural networks because if you start from a finite set of neurons, you do this is essentially plain gradient descent, and it's known to get stuck. Okay, so if you initialize it incorrectly, you will get stuck. Okay, so it's a problem where the dynamics has some bad stationary points. Okay, so having a statement about the gradient flow that converges the global optimum means that you initialize it correctly. Okay, because if you initialize it not correctly, it won't work. So for this, Okay, so of course the statement is much more precise in the paper, but we need some technical, assumptions about like differentiability and regularity, which I want to avoid mentioning. But let me mention the two key ingredients because they tell us, at least like Lénaïc and me, that we are not doing something totally trivial. It does not always work. So if it was always working, there will be some issues. And here we need two assumptions which are critical. And if you remove them, then we have counterexamples. The first one is homogeneity. Okay, it was highlighted by people before. And you need your function psi to be either fully homogeneous or at least partially homogeneous. So for neural networks, this is true because you're always homogeneous with respect to the last layer. And if you use the ReLU, you're even better, you homogeneous with respect to the entire thing. Okay, so what I will show later for the analysis part, we use the ReLU because it makes our life easier to be fully homogeneous. But at least for this analysis now, I just need partial homogeneity. So meaning that this is okay. So this is one assumption. You need some form of homogeneity. And the second assumption is that you need to initialize correctly. And the idea here is that you simply initialize exactly in the way that people are doing for neural networks, like everything totally random and uniform in all directions. So if you initialize with Gaussians, this is true. And this is what we need. We need that you initialize in all directions. And then if you assume this, then we can show, of course, with a lot of other assumptions that you do converge to the global optimum. All right, so one big caveat, and I will say it over and over again, this is very qualitative, okay? I wish I was able to tell you how many neurons you need to achieve that behavior. I don't know. I wish I knew how fast it converges. I don't know, okay? So it's very, very weak, but at the moment it's the best we can do. All right, so let's look at some simulations, okay? So this is like toyish. So we're doing like neural networks in 2 dimensions. And so this is a model that we have. And since we use ReLU, so the max function here, but the positive part function here, then this is homogeneous. And I'm going to plot the neurons through the directions only. Okay, neurons are plotted, and what you care about, since you homogeneous, is that you achieve the correct directions. So we we generate data from some neural network with 5 neurons. Okay, those are the 5 directions that have generated data, and we run the stochastic gradient every time with a new random sample and with a very small step size, and we initialize the dynamics with either 5 neurons, 10 neurons, or 100 neurons. So since I have generated the data with 5 neurons and with no noise, we know that the global optimum can be achieved by 5 neurons. Okay, so it's enough to converge. And as you can see, when you launch the gradient flow, so you start uniformly close to 0, and then you're going to converge to a point which is not the global optimum. Okay, so it's a case showing that you can get stuck empirically with the gradient flow for neural networks. What our results suggests, okay, and let me be clear, this is just a suggestion. There's not a proof that for 100 neurons is enough. We need the number of neurons to be big. Then you start, and they're all going to end up in the correct locations. Okay? This is what's happening when you have 100 neurons. Okay, so you over-parameterize a lot, and then all of them end up in the correct direction. The surprising aspect is when you get like only 10 neurons. So it's just like a constant factor more than what you need to get the global optimum, and that's enough. And you get it quite robustly to get the global optimum. Okay, so this is like a bit surprising. I have a small video showing this for 100 neurons. So you start, and the neurons move in weird ways, and they end up converging. As you can see, the dynamic is very weird. Okay, so neurons move, but at the end they end up all converging. Okay, so what our research says is that if the neurons, you have infinitely many of them, is doing what you see in the plot. So we are still missing really what's happening with a finite number of neurons, but it's still like hard to do. All right, so this is a summary of what we have seen so far. We have seen so far, if you do like neural networks, for example, like ReLU type of things, then if the number of neurons tend to infinity, then the gradient flow does converge to the global optimum of the risk, so which is good. Okay, so what we need is that we have a well-spread initialization, and again, there is no quantitative results. So what I've mentioned earlier, if you do like a single pass LGD, okay, then more or less it will follow the gradient flow if the step size goes to 0. But the issue is that it does generalize well, but it tends to underfit. And it's not that people in practice, you always do multiple passes. So now what happens if you do multiple passes, you end up minimizing the empirical risk. Okay, so now you may overfit. So now the question is, do you overfit or not? Okay, so can you make sure that you don't overfit? So this is the question I'm going to try to answer for the rest of the talk. We're going to assume that if you launch the gradient flow, you're going to converge the global optimum, and we're going to show that the global optimum is correct. All right, so this is, we are in a regime which is now called the interpolation regime, because we are minimizing a function, which is the average over n observations, okay? And we have m neurons. So since we have d plus 1 parameter per neuron, we have a lot of parameters. So you have many more parameters than neurons. So you should expect that there are many potential edge functions that will achieve 0 loss. Okay? So this is like well known. And there are many people looking at this in terms of optimization. So the question is, to which edge do we converge? Okay, so it's the good. So we know we converge to the global optimum of the risk. Okay, so we know we're going to achieve like 0 loss, but which one are we converging to? So it's really the key question, and this is often called the implicit bias of gradient descent. Okay, so we select one of the minimizer. Which one is it? All right, so what people know, and this is a very nice size of work by Surya Gunasekar and colleagues, and showing that typically when you do HGD on some parameter vector, you end up in the minimum Euclidean norm solution. So the implicit bias, at least for linear models, okay, so implicit bias typically is the minimum L2 norm solution. Okay. So what is quite funny is that it's very hard to do for the square loss. It's not really true for the square loss, it's a bit more complicated. And it's very easy for the logistic loss if you assume like some separable data. So we're going to follow what they do and consider the separable loss. All right, so now we go back to, let's do like a detour towards like finite dimensional problems. Okay, so this is essentially the work of Soudry and colleagues. So you minimize logistic loss, this is logistic loss, and we're going to assume that the data are separable. So they exist, hyperplane going through the origin, separating the data. And we're going to make one extra assumption, which is very classical in this area, is to replace the 0 here by the 1. Okay, so if this is true for 0, with a strict inequality, you can assume this is true with a 1 by just rescaling the norm of the vector. And this is like old school, like machine learning from 95. And so what you can show is that, so this is also a curve from 95, when you have the 0-1 loss, the hinge loss in red, and the logistic loss in green. And what you can see, to achieve 0 loss, okay, for the logistic loss, to achieve, for the hinge loss, you can achieve 0 loss if you're on the right side of 1. Okay, so as soon as for your theta this is true, then you don't move anymore, you have a 0 hinge loss. But when, for the logistic loss, since it's still like only 0 at infinity, to converge, you need to send your norm to infinity. Okay, this is the intuition behind those results, that to minimize the logistic loss for a separable problem, you have to diverge to infinity. So this is a good trick for students. Okay, you hack them to implement gradient descent for a separable logistic regression, and typically they are not super happy. And they have to understand why they're not happy, which is like a good thing to learn. Yeah, okay, so in more details, so this is the work of Soudry and colleagues again. If you use gradient descent, then you converge to the so-called maximum margin separator, which is a formula over there, but the one that people, the formula that people are typically familiar with is among all the data such as this is true, then you take the minimum N2 norm. Okay, so this corresponds to essentially that hyperplane here. Okay, so it's also a nice curve from going back from the 90s, and if not earlier. And so, so what Soudry has shown is that if you do logistic regression on separable data with gradient descent, you end up with to the maximum margin separator, or the direction of the maximum margin separator. Right, let's see what it does for us. Okay, so for us, we have two sets of parameters. We have the theta 2 and theta 1, and our goal is to see what's happening when m goes to infinity. So we'll see two different regimes, one where we learn over the last layer only, okay, and one where we do gradient descent with respect to the two layers. Okay, so this is one partial learning, one full learning. One will converge to kernel machine, and one will do like feature learning. Well, let's do the kernel regime. So this is like almost obvious given what I've said so far, given previous work. So this is my prediction function. My input weights are considered being fixed. I sample them, then they're fixed for optimization, and I optimize only over theta 2. So what I have here, I have a linear model, okay, with a set of features, which is just like of dimension m. Okay, so now I can use as a result from Soudry and colleagues, where you're going to minimize, you're going to converge to the minimum N2 norm solution. Okay, so now we are back in familiar territory. I'm doing linear, I fit linearly, okay, with a square norm penalty. So this has to be linked with kernel methods, okay? And this is indeed linked with kernel methods. So if you look at the feature vectors and compute the dot product between phi of x and phi of x prime, you realize that you get a very nice average like this. Okay, so an average of those functions. So when m goes to infinity, the kernel goes to the expectation over the randomness of theta 1, which is this. So eta typically is uniform on the sphere, or Gaussian if you want, and you get converges to a kernel method. And in fact, this is well known from the random feature analysis that have been like started by Neil in 95 and Raimi and Reich in 2007. Typically, the way they use it is they start from a kernel, which is an expectation, and approximate it using an empirical average. Here, we use it in the other direction. We want to study the limit when m goes to infinity, and we end up with a kernel method. Okay, so this is to be expected. We have like a linear model, okay, so we converge to a kernel method. And now the question is, what is the limiting kernel? So you can show that it's a kernel of smooth functions. Okay, typically, this is well studied, like in a paper of mine, like from 3 years ago, and this has been studied before as well, that those kernels, which are called dot product kernels, lead to smooth functions. So the very unintuitive part is that a single neuron is non-smooth here, but when you take the limit, you get smooth functions. Okay, this is so a single neuron is not part of the Hilbert space. Okay, so you have to be careful here. We're going to learn very smooth functions, and I will show examples in a moment. So what is our informal theorem that we have is that if m goes to infinity, then the gradient flow does converge to the minimum RKHS norm solution. Okay, so it's almost straightforward from what I've seen before. Nothing really new here. You can be quantitative if you want. Okay, so this is something that you can do because you are in the convex world now. And there's also a nice paper by Montanari in the context of double descent. And one point which you should really be clear about is that it's a purely theoretical argument. Why? Because as soon as m is bigger than n, you should use a kernel. Okay, which will lead to like a problem of dimension n, and not keep adding neurons where m goes to infinity. Okay, so in practice, it will never do this. It's just a way to analyze what it does when m goes to infinity. So this was the kernel regime. Now let's study if you optimize over the two parameters, both layers. The hope is that it does something interesting. And to analyze what it does, I have to like go back a bit to the RKHS norm that I've just defined. It turns out that you can define the norm. So the norm defines the space of functions, and the space of function are averages of the single neurons, okay, with a penalty on the squared norm of the weights. Okay, so you average your neurons, okay, and you put a square norm on the weights. Okay, so this is the exact same kernel as before, and it gives you smooth functions. What you need to analyze the regime when you optimize over both layers is to replace the square norm by the L1 norm. Okay, it's called the variation norm, and this was introduced by Kokova and Sanguinetti. And this is, so since you have the L1 norm, you can start to have measures which are singular. Okay, you can have single neurons and so on. Okay, so this space of functions does include very non-smooth functions. It's much bigger than the RKHS. And as I've shown like 2 years ago, you can adapt because you have an L1 norm penalty, so it's supposed to adapt a bit more than the L2 penalty. And what we showed is that if you let the number of neurons go to infinity and you optimize over both layers, this is the informal theorem because we need more assumptions, you converge to the minimum variation norm. Okay, so you know where you're converging to, and this is in a sense the end of the double descent curve that Michel Belkin and others have looked at. So if you increase the number of parameters, your gradient descent algorithm will converge to a place which does something which can be interesting. So here, in the context of two-layer neural networks, we say it does converge to the minimum variation norm. So we know exactly what it does at the end. Interesting aspect is that this does learn representations, because at the end, typically, because of the L1 norm, you get a sparse solution. So this does learn representations. And the funny aspect, I think the key aspect is that I don't know of any like polynomial time algorithm to solve that problem. Okay, so it's a norm, but the norm is which is hard to represent. And here, by doing like using particles and using like finite M, we have a way to approximate the solution of that problem. Again, it's only qualitative. I don't know how big M needs to be. So let's look at some plots. Okay, so about this like optimizing over two layers. So on the left, I will plot on the space of parameters, the neurons. On the right, in the space of predictors. So on the left, you see neurons moving along. Okay, so you see the problem in 2D with a bias, a constant term. So you have three parameters, and you see the neurons moving on the left, and so they move a lot. And on the right, you see the prediction function, which is moving along. So I will show it again, but what's key is that the final prediction function has like piecewise linear boundaries, because you end up with a finite number of neurons, because all neurons here coalesce, almost all neurons here coalesce to the same one. Oh, let me stop it. Okay, so what you see here on the right, that piecewise affine functions. Okay, this is to be expected. And here the neurons, they started to go all over the place and end up converging to the same place. Okay, this is just to illustrate the results, both on the parameter space, the neuron space, which has no real meaning in terms of intuition, and the prediction space, which is here in 2D. And now we can compare with the last slide. So we're going to compare the L2 regime, which corresponds to only optimizing over the last layer, to the L1 regime, which is optimizing with respect to two layers. So let's see what we get. So no, we have to press there. Okay, so on the left, this is a kernel machine at the end, and here at the end, this is like the neural network. Okay, so let me stop here, it's not moving anymore. So here you see the two different behaviors. Okay, so on the right, like in the previous slide, you have a piecewise constant function because you end up with a finite number of active neurons. Whereas, and this is a non-smooth function because of the kinks over there. Whereas in the kernel regime, although you combine non-smooth functions like the ReLUs, by averaging, you end up with a smooth function, which is what you have here. Okay, and the dynamics. Oh, sorry, if I start again dynamics, yeah, so there's not much you can see in the dynamics, but the key here, the key difference is the last part. All right, so just one more comparison is that, so what we show with Lénaïc as well is that if you're, since you're doing like feature learning, you want to check that if your problem has some feature selection like feature in it, then can you recover it? So what we, just for testing, we're going to take like something in higher dimensions, so not very big, where dimension 15, where the two coordinates will essentially will be where all the signal is, and this is, and whereas all other coordinates are totally at random. Okay, so I generate data like this. The labels are just like the colors, and this is a location in 2D, and I add some random directions. So here, to do well, you better learn what those two directions are. You need to do some form of feature selection to do correctly. And this is what you get when you increase the number of samples and you plot the test error. If you optimize over both layers, you convert like reasonably quickly to a good test error. Whereas if you optimize over both layers, so you don't do feature learning, you only optimize over the last layer, sorry, then it goes much slower. So if I were to increase n much more, then this orange curve will tend to 0. Why? Because we do have a kernel machine with like a universal kernel, essentially. So at the end, you can learn everything. But the problem is that you're still faced with the curse of dimensionality because you don't do feature selection. So the orange curve will tend to 0 much slower than the blue curve. Right. So to conclude, to summarize what I've talked about, so I've tried to provide a qualitative analysis of gradient descent for two-layer neural networks. Okay, so, and the key aspect is that if you let a number of neurons go to infinity, we can provide results showing that you get a global convergence in that setup. So it's still a complex dynamics where stationary points which are not globally optimum, but if you initialize correctly, and here totally randomly, but uniformly in all directions, then you're safe. And in the context of ReLUs and separable data, we show that we can characterize where we converge to. Okay, and so this is for the max margin setup. So here, at the moment, as I've mentioned, it's only qualitative. We don't know how to, but regarding time, we don't know how fast it will be to converge, and we don't know the number of neurons. So open problems, of course, start to be quantitative, and this is much harder than I thought. Okay, so to be fair, in March, when I thought, oh, I'm going to be stuck at home for 6 months, then I'm going to crack the problem with Lénaïc. Didn't work. Okay, so maybe we have to be confined once more to solve that problem. It's difficult. Okay, so it's expressed in a simple way. Okay, so if you take that simple ReLU, let the number of neurons go to infinity, how fast does it go to the minimum risk, and how big M needs to be. Even a very simple problem is difficult, okay? Even after all the simplification that I've done, okay? So gradient flow instead of gradient descent, like just 2 layers, is already difficult. Of course, we want to go convolutional, okay? Because this is important. And of course, here I'm super non-deep. Okay, so I've decreased my shallowness level by going from 1 layer to 2 layers, but clearly there is a lot of work to be done to try to see how you can go beyond 2 layers. And this is difficult because all these separability assumptions are not satisfied anymore, and hopefully we'll be able to do that in a few months or years. Thank you for your attention.
Thank you, Francis. I appreciate it. Very nice talk. So let's see if there's any question for you.
I have one.
Please go ahead.
Yeah. Hi, Francis. Enjoyed your talk. I have a bunch of questions, so that's why I was stumbling, but I will only ask one. You showed that your neurons are converging to your model. Mm-hmm. How do you go back and then get the best model possible in a two-layer?
That's very good. Okay, so yeah, so we have a very good point. Okay, so essentially once you are, let's take this one. Yep. So once you're there, okay, the question is, how do I get to a short model? Okay, because if all neurons are the same, maybe I should not keep the 100 neurons, but reduce the dimensionality. Okay, so the first answer would be you don't care. You predict with the 100 neurons. That would be like a bit inefficient. And so here we have not looked at it, but you could imagine various like clustering, various ways of clustering the neurons or sampling the neurons. I don't know. So I think we have not explored it. The reason being that in practice, what we believe is that you just need to be a constant factor away than the best number of neurons. Okay, in some setups, and if you're just a constant number away of the, if you have 10, it's okay. Okay, when you have 10 neurons instead of 5, you don't really care about the factor of 2. So we try to understand that regime where the problem that you mentioned is not so problematic. But clearly, if you want to really over-parameterize, let's say your Google or Facebook, you want to kill the whole forest in one simulation, yes, you will need to reduce the number of neurons after training. And clustering could be an issue, could be a way of doing it, but there are probably other ways.
So you mean the quality of the clustering will be a guided motion so that you would get the best model with the best generalization error? Is that what you're suggesting?
Well, I think if all neurons have the same directions, have only 5 directions, if you do k-means on the sphere here, you should expect to get like 5 good neurons.
I see.
What I meant.
Oh, I see. So the error of what neurons get misclustered would be a measure.
Yeah, never. So here, okay, in that like super 2D simulations, all neurons are in the correct directions. So if you do k-means on the sphere here, it will be perfect with 5 clusters. But clearly, this is like super idealistic. So if you add noise, so if you start to add noise into the equation, then it will be a bit harder to cluster. So that's why we have not explored it. I think it is interesting, but we have not explored it yet.
Well, thank you, and thanks again for giving this nice talk.
I have a question. So if I understood correctly, you said that in several problems we converge to the model that has the minimum norm.
Yep.
But usually in optimization, we add regularization to force the model to have certain small norm, either sparse or L2 norm.
Yep.
So I was wondering if you could give us a little bit more intuition about why we're converging and if in that case would be redundant in some sense.
Okay. Very good question. So let me go there. So for the random feature, for the kernel regime, this is in a sense totally useless. If you have a convex problem, okay, and you want to minimize, you have a linear model, okay. So let's say I want to solve this problem, okay. I want to have the minimum L2 norm so that you're separable. There are many ways of doing it. Some convex ways, okay, and clearly here using like particles is kind of useless, and this is what I'm trying to hint here. So letting m go to infinity is useless. Why? Because you don't need to represent your problem in an infinite dimensional space. You can reduce to the size, to the number of observations. Okay, so for that norm, which is like Euclidean norm, essentially a Hilbertian norm, you don't need to do this. But for the other norm, where it's also a norm, variation norm, but this one, I don't know of any polynomial time way of representing it. So if I were like in finite discrete setup, sure, I have a minimum L1 norm solution. I could run my favorite like proximal thing or dual algorithm. But here, because I have in infinite dimensions and the norm is not Hilbertian, I don't know of any way of doing it in a different way. Okay, so this is what I was trying to say here. I don't know how to do it directly. And one interesting aspect here is that having particles allows you to do optimization. At the moment, since I don't know how big m needs to be, it's more like hand waving. I know if m is big enough, it's fine. But the hope is that we can have a detailed analysis of how small m needs to be. Okay, so so this is really the issue. If you take this minimum norm algorithm and try to launch your favorite convex optimization algorithm, it won't work here.
So if I may ask something on related to this. Yeah, can you hear me?
Yeah, please go ahead.
So is there, I remember, I haven't followed all these works very closely, but I remember that there was a lot of discussion earlier about SGD, like the randomness of SGD creating some regularization, and also the other possibility of adding a noise to your own gradients, you know, doing something like Langevin dynamics here. Is there any result here where there's randomness in your gradient that actually regularizes or helps you?
Yeah, so there are, okay, so here, when I talk about the gradient flow here, what is this? For gradient flow, so if you use the exact SGD, so where the noise in the gradient is of the order of the step size, then you go to the gradient flow. If you add more noise, okay, like square root of gamma, where gamma is the step size, then you convert to a Langevin diffusion. And people have done that. I think there's a very nice paper for that, this exact problem. Nice paper by Songmei, Montanari, and this is what I'm citing earlier, where they do add this, so they convert to a diffusion, okay? So, and by using this, they get stronger results. So they can quantify the number of neurons, but they don't convert to global optimum. They convert to a distribution, which is like a smoothing of the actual thing, okay? So you can do that, and in fact, this is one way of getting some guarantees, but the problem is that if you let the noise variance go to 0, it explodes. So I think the issue here is that the global optimizer of those dynamics are singular measures, okay? Right. And so, and yes, so because the limit points are singular measures, this is where it's much harder because for that problem, it's really the issue. So either you not cheat, but add density everywhere, okay? And people have done that. So if you add density everywhere, then you can show like global linear convergence of the problem, but you're not solving what you care about, okay? So this is really like, I've talked to mathematicians, and really this singular measure aspect is really what kills you.
Right, great, thank you.
Okay, is there any other question for Francis? Okay, if not, let me thank again Francis for giving this great talk. Really appreciate it. This talk is going to be recorded and it's going to be available on our ML seminar website. Thank you, everyone.